You're online.
Yes.宋老师可以看到我的这个共享的页面吗？PPT 吗？
可以的。
好的，好的。
You can now start the webinar, please.
Okay. Hello, everyone, all the audience. Welcome to IABSE's webinar today. Good afternoon in Europe and good evening in China. So this is the IABSE webinar, Innovation Design of the Huangmaohai Link, China. My name is Tongji from Tongji University, China, and I'm the moderator of this webinar. First of all, let me introduce about IABSE. IABSE, in short, it is the International Association for Bridge and Structural Engineering. The website was www.iabse.org. And its mission is to exchange knowledge and advance the practice of structural engineering worldwide, including all aspects in structural engineering and all types of structures and structural materials and all aspects of the construction process. It has 100 countries and over 65 delegates, national groups worldwide. IABSE is a scientific technical association comprising members in 100 countries and counting 60 plus national groups worldwide. It was founded in 1929. It has its seat in Zurich, Switzerland. IABSE deals with all aspects of structural engineering, as I read before, including science and art of planning, design, construction, operation, monitoring, and inspection, maintenance, rehabilitation, and preservation, demolishing and dismantling of the structures, taking into consideration technical, economic, environmental, aesthetic, and social aspects The term structures includes bridges, buildings, and all types of civil engineering structures composed of any structural material. The president present is Harshavardhan Sabaro from India, and its objectives and tasks. It has the following objectives to promote cooperation and understanding among all those concerned with structural engineering and related fields by worldwide exchange of knowledge and experience, to encourage awareness and responsibility of structural engineers towards the needs of society, to encourage actions necessary for progress in structural engineering, to improve and foster cooperation and understanding between organizations having similar objectives. So for this purpose, the association will organize these conferences worldwide to publish the high-quality journal SEI, Structural Engineering International, publish books reflecting the work of its technical groups, creates technical groups as required by new needs and technological progress, offers the possibility to join activities within national groups of the IABSE, offers a program for young engineers, presents annual awards. And this is the annual meetings. It will held preceding the Congress every year. This year in spring, there are two meetings. In spring is symposium, and in autumn will be the Congress. This year was in Copenhagen in April, and in this September will be the Congress will be in Incheon, Korea, and the early bird, please notice that the early bird registration is already extended to July the 19th, so you can register now before July the 19th. And for next year, in spring meeting will be in Guwahati, India, and the abstracts will be closed before July the 15th. So we will have 10 days, even have 1 week. So please submit if you have abstracts to Guwahati symposium. And 2027, the Congress will be in Milan, Italy, on September 1st to September the 3rd. And the IABSE has many publications, including Structural Engineering International, the journal SEI, and the IABSE bulletins, including every the research results for every task groups, and case studies, guidelines, special publications, and also for every conference, including symposium and congress, will be proceedings. And we have national groups. We referred before that we have about more than 60 national groups. We will have meetings before the Congress in the annual meetings. And this is the meeting of national groups. And aside of that, there's IABSE technical activities. We have 6 technical commissions named Commission 1, Performance and Requirements, Commission 2, Conceptual Design, Commission 3, Structural Analysis and Evaluation, Commission 4, Construction Methods and Processes, Commission 5, Existing Structures, and Commission 6, Sustainability. And then we have task groups for special purpose. And especially we have Young Engineers Program, YEP, and also have students membership, Young Engineers activities. So welcome to IABSE eLearning. The webinar is included in this IABSE e-learning program. Webinars are free for all. You can up to the website www.iabse.org events to watch the webinars. And every November we have IABSE Awards, and including gala dinner and some sightseeing. And this is the awards last year. So welcome to it is IABSE so unique. So join us. Welcome to be a member of IABSE. So so today the webinar titled "Innovation Design of the Huangmaohai Link, China." So the speaker of the webinar is Zhao Lei. He is a professor level senior engineer, a chief engineer of the Bridge Department, second CCCC Highway Consultants Co. Limited, China. After graduating with the master's degree, he worked for 18 years in engineering design. During this period, he participated in major projects such as the Hong Kong-Zhuhai-Macao Bridge, Nansha Bridge, Shenzhen-Zhongshan Link, Huangmaohai Link, and Shiziyang Bridge. So please start.
Okay.
Please, Mr. Zhao.
Thank you. Okay, thank you. Wait a moment. Hello, everyone. Good afternoon. Thank you, Professor Xu, for the introduction. I'm Zhao Lei from HPDI, Chief Engineer of Second Major Bridge Department. I will present the Huangmaohai Link on behalf of our project team. Our presentation is organized into 6 parts: project overview, construction challenges. Wait a moment. Construction challenges, bridge aesthetics, structure innovation, engineering implementation, achievements and benefits. Let us begin with part 1, project overview. To understand the Huangmaohai Link, it is helpful to consider its strategic context within the Guangdong-Hong Kong-Macao Great Bay Area. The Great Bay Area includes 11 cities with a combined population of over 86 million people and a GDP exceeding $1.9 trillion. For many years, the western part of Guangdong province, including cities like Jiangmen, Yangjiang, has faced the transportation limitation that affect economic integration with the more developed core area. The vision for Huangmaohai Link was to create a new transportation link that would improve the connectivity and support a more balanced economic development across this area. Located at the core of Guangdong-Hong Kong-Macao Great Bay Area, the Huangmaohai Link serves as a westernward extension of Hong Kong-Zhuhai-Macao Bridge. Together with the Hong Kong-Zhuhai-Macao Bridge, the Shenzhen-Zhongshan Link, the Humen-Nansha-Huangpu Bridge, the Huangmaohai Link contributes to an important cluster of transportation infrastructure connecting Guangdong coastal economic belt. The network of bridges and tunnels creates an important improved transportation system that links the coastal region, enabling better movement of people, goods, service, and ideas. Let us now describe the engineering scale of this project. Stretching 31 kilometers in total length, with 14 kilometers crossing the sea, the Huangmaohai Link represents an investment of $1.8 billion. The project includes several notable structures. West Channel Bridge, the world's largest three-pylon cable-stayed highway bridge, with a main span of 720 meters, crossing eastern and western channels. There's also a 700-meter cable-stayed bridge spanning the Dongdong waterway. The project also includes a steel box continuous girder bridge with 16 consecutive spans of 1,000 bridge each, totaling 1,600 meters in length. The project included 2,521 meters of twin tunnels designed for divided two-way six-lane expressway with a structure clearance of 15.5 meters wide and 5 meters high. An important aspect of Huangmaohai Link is the construction timeline we achieved. Construction commenced in June 2020. In December 2024, the project already was officially open to the traffic. Despite the challenging construction conditions, the project was complete and open to traffic in about 4 years, setting a remarkable benchmark known as Huangmaohai speed. Now, moving to part 2, construction challenges. We addressed the 4 major technological challenges: typhoons, marine environment, ship collision, special shaped pylon construction. First among our challenges was wind resistance. The Huangmaohai region is located in a typhoon-prone area. Since 1949, 84 typhoons have made landfall in this area. Most recently, in September 2024, super typhoon Kong-Macao struck, reaching level 18 intensity with wind speed exceeding 16.5 meters per second. Our design-based wind speed was set at 46.1 meters per second. Through aerodynamic design and vibration control technologies, we achieved the performance that exceeded these requirements, as I will describe later. The second major challenge was ensuring durability in the marine environment. The Southern China Sea presents a high temperature, high humidity, high salt environment that can be corrosive to steel and concrete. The seawater chloride ion concentration in this area ranged from 5,410 to 20,480 milligrams per liter. Without appropriate protection, chloride ions can penetrate the concrete. Chloride reinforce and affect the bridge's service life. Our solution was a comprehensive layered anti-collision strategy, adapt to different exposure conditions along the pylon height. This approach is designed to help the Huangmaohai Link reach its intended 100-year structure life marine type environment. Our third major challenge was ship impact protection. The Huangmaohai Link across 3 navigation channels with significant marine type traffic. The West Channel Bridge is designed to accommodate 13 DWT vessels. The design impact force for this scenario is 81 megatons at a velocity of 3.39 meters per second. Our solution including strengthening the pylon along with the anti-collision fenders around the pipe foundation and an active anti-collision warning system. This multi-layered approach is intended to ensure safety for both the bridge structure and the marine type traffic. The fourth challenge was pylon construction. Our special shift hyperbolic reinforced concrete bridge pylon presents special construction difficulties. Unlike conventional pylons with constant cross-section, each section of our hyperbolic pylon has different dimensions. The cross-section of the pylon starts as a circular section with 18 meters at the base, gradually transition to a diameter to a rounded rectangular with width of 10 meters at the deck level. Further upward, it taps into a circular section with 9.5 meters diameter, then enlarged to 11 meter diameter at the top. This varying geometry presented challenges in three areas: reinforcement construction, formwork construction, and climbing formwork construction. For reinforcement, traditional scattered rebar bending had bad efficiency limitation, quality control consideration, and safety consideration for work at height. For formwork, the all-steel large formwork system had reuse limitation and cost consideration when every section differs. For climbing formwork, traditional design methods require adaptation. We needed to address how the climbing form could adapt to irregular tower wall and how the climbing trajectory could accommodate to the changing geometry. The solution we developed represent important construction navigation for the project, which I will detail in the engineering implementation section. Now we move to part 3, bridge aesthetics. We sought to create a masterpiece that would feel appropriate to its environment and contribute positive to the region. Our pylon design considered the regional and cultural context. The Great Bay Area and the Guangdong province have a maritime heritage and a culture of openness and innovation. From this context, we select the circle as the core design element, reflecting the forms of the lighthouse and the shape masses characterize the maritime region. The 5 pylons share a consistent design style, dynamic, elegant, and streamlined, with a minimalist yet sophisticated aesthetic that also meet structural requirements. Their distinctive and iconic C-sharp harmonize with the surrounding environment, making the most recognizable feature of Huangmaohai Link. For the alignment design, we implemented a C-curve road. This was chosen for both driving comfort and geometry continuity. As drivers crossing the bridge, they experience a journey that offers a changing perspective of the main bridge. This creates the visual effect of bridge flowing with the coastal contours. The approach section curves gracefully, allowing driver to approach the main bridge gradually from a dynamic perspective, presenting the vista where the bridge sweeping over the bay, harmonizing with the natural environment. The pylon retains the original color of concrete, forming a gradual fusion with the foggy sky of the sea area. Now we arrive at part 4, structure innovation. Let me now describe 7 structure innovation developed for this project. First, hyperboloid single column pylon structure. We developed a hyperboloid single column reinforced concrete pylon. The design varies along the height. The upper pylon widens for anchorage space. The middle pylon narrows to reduce the girder width. and the lower pylon widens again for improved bending resistance and collision protection. It features superior static performance and outstanding wind stability, realizing the harmony of mechanics and aesthetics. Second, central auxiliary cable technology. 3 pylon cable-stayed bridges have inherent vertical stiffness consideration because the middle pylon lacks the end restraint from anchorage. To address this, we carry out a number of comparative studies of different options, such as cross-section, cross-cable system, and high-low pylons. Having evaluated more than 10 proposals, we determined that the 5 auxiliary cable solution features the lowest cost and a simple structure. Lowest cost. 5 pairs of central auxiliary cables solution reduce the deck vertical displacement by 39%. Third, multi-point energy dissipating system. We adopted a system with elastic restraint at the middle pylon and viscous dampers at the side pylons. Under seismic action, pylon-based bending moment is reduced by 42%, while girder and longitude displacement reduced by over 15%, reducing expansion joint requirements. Fourth, separate twin box girder aerodynamic. Through wind tunnel testing, we optimized the separated twin box girder section, achieving a flat critical speed of 95 meters per second. Having withstood the severe test posed by the super typhoon Huangmaohai, the maximum wind speed measured at the top of the tower was 78 meters per second. The system has demonstrated the effectiveness and reliability of its wind-resistant control technology. The biggest challenge of twin box girders lies not in flat, but vortex-induced vibration. Furthermore, the design of Huangmaohai Bridge, coincidentally with the vortex vibration instead of which I know narrows bridge, drawing extremely high attention from the whole society. To resolve the vortex-induced vibration, we enlisted 3 universities to carry out hundreds of tests. After multiple rounds of comparison and selection, the wind-resistant measures shown in this figure were ultimately adopted. In addition to the wind fairings, horizontal flow deflectors, vertical vortex suppression buffers are installed between the twin box. Furthermore, the inspection trolling track under the deck are removed. A compact size track is directly arranged above the wind fairing. With all these measures implanted, the vertical acceleration is controlled below 0.5 meters per second square. Fifth, construction vibration control. We developed a temperature pier plus TMD combined control technology. This system performed well during Typhoon Marias. When the structure withstood the level 8 wind during 300-meter cantilever construction. 6. TY-shaped bridge piers. Our pier design reduce beam cantilever length and weight, provides important anti-collision capability, and minimalized pie cap size while reducing the water blocking ratio. Seventh, middle approach bridge vortex control. For 1,600-meter approach bridge, we developed the transverse connection box plus TMD hybrid vortex control technology that saved 1,000 tons of steel compared to the aerodynamic measures alone. Part 5, engineering implementation. Innovation extends beyond design to construction methods. First, digital design and industrialized construction. For our variable cross-section patterns, we developed a 3D digital design and industrialized molding technology. For reinforced cages, features equal spacing configuration, midway anchoring, and integral hoisting with precision docking at height. Rather than works bending individual bars at the height, we fabricate complete cages in controlled condition, then transport and install them as unit. This improves the quality, safety, and efficiency. Second, hyperbolic formwork and climbing system. We developed the digital design, precision manufacturing, assembly, modeling technology for hyperbolic formwork. Our adaptive climbing formwork system optimized the formwork turnover. We complete 14.5 pylon segments using only 3 formwork size, improving the construction efficiency by 30%. Third, ultra-wide spallied steel box girders. We propose an integral assembly method with dedicated jigs and developed a micro deformation stress-free control technology. We achieved the transverse slope deviation accuracy within 0.07%. Fourth, IoT-based tunnel monitoring system. For our tunnels, we developed an early warning system using solid-state LiDAR for 3D rock deformation identification. This enables 24-hour automatic monitoring with edge node interment accuracy and fault recovery, improving efficiency by 85% and enhancing safety during construction and service. Part 6, achievements and benefits. First, environmental protection. Environmental considerations were important throughout the project. Through noise and vibration control, wildlife disturbance minimization, and economic preservation measures, we implemented a green construction practice. The Huangmaohai Link demonstrated that major infrastructure and environmental protection can be pursued together. Second, transportation benefits. The most immediate benefit is improved connectivity. The Huangmaohai Link creates a western transportation route from the Great Bay Area core, reducing travel time between Zhuhai and Jiangmen by 30 minutes. For many people, this means reduced commuting time, lower transportation costs, and improved access to opportunities. Third, social value. This link improves connectivity between Western Guangdong region and the Great Bay Area core. It supports economic development, social progress, and cultural integration, benefiting industry from tourism and energy to fisheries, and connecting overseas Chinese communities. The Huangmaohai Link is more than a transportation project. It contributes to a more balanced and integral future for the region it serves. This is a video of the site. And this is a 3 minutes short video about technical detail. Please watch.
Situated in Guangdong, China, connecting Zhuhai City and Qianmen City. It serves as the western extension of the Hong Kong-Zhuhai-Macao Bridge. The 31-kilometer-long Huangmaohai Link comprises the Huangmaohai Bridge, the Xishan Tunnel, the Xiangshan Tunnel, and 4 interchanges. The Huangmaohai Bridge consists of the West Channel Bridge, the Central Approach Bridge, and the East Channel Bridge, located in a strong typhoon-prone area with high-designed road speeds and crossing 3 busy shipping channels. The project faced severe construction conditions and significant engineering challenges. Aesthetics design. The project pursues a minimalist and elegant design style. Its marine section features smooth, large C-shaped route, while the cable-stayed bridges adopt a scheme of single column pylon plus split speedbox girder. The bridge pylons feature an innovative double-curved surface design, combining a solid foundation with a streamlined silhouette. The 5 elegant cable-stayed pylons stand tall above the sea, achieving a harmonious integration of structural mechanics and architectural aesthetics. Structural innovation. The project introduced a vertical stiffness enhancement technique involving the installation of 5 pairs of central auxiliary cables at the central pylon. This innovation reduced the sum of the maximum vertical deflections of the main girder by 39%. A high-performance structural system was developed for the 3-pylon cable-stayed bridge in the typhoon zone. This system features elastic cables at the central pylon and vicious fluid dampers at the side pylons longitudinally, coupled with an aerodynamic control technology for vortex-induced vibrations of the ultra-wide split steel box girder. These measures significantly improve the structure's wind resistance. Engineering implementation technology. The design construction integrated the technology and implement for the double-curved faces shaped tower in the project. It's developed, which realizes reinforcement parts process and installation with works efficiency improved by around 50%. Thus, the safety risks of works aloft is greatly reduced. Sustainability. Adhering to principles of sustainable development, the project optimized its design to protect the ecological environment, minimizing construction noise and disturbance. This effectively safeguarded local wildlife resources, such as egret and fish. Following its completion and opening to traffic, travel time between the eastern and western banks has been shortened from 70 minutes to 30 minutes. This has effectively driven the integrated development of the less developed western and coastal regions of Guangdong with the Guangdong-Hong Kong-Macao Greater Bay Area, painting a harmonious picture of coexistence between engineering, humanity, and nature.
Okay, that's all. Thank you. Dr. Xu, you are mute.
Thank you, Mr. Let me see if there's any questions from the audience. For any questions, please feel free to post it under Q&A.
So we are still waiting for the questions. Can I ask a short question?
Yeah.
Mr. Zhao, thank you for the great presentation. I'm Mingming Song from Tongji University. I'm also the General Secretary for the Chinese group, National Group of China. So,
Okay.
so Huangmaohai Link, it has a very special design. It adopts three pylons, three towers design. What's the biggest challenge of this design compared to the more common two-tower design for this cable-stayed bridge? Thank you.
I think there is two challenges. First is stiffness. With the one column pylon, is more flexible, so we have to more concentrate on the stiffness transversely and longitudinally. Second is aerodynamic. As I was mentioned before in my presentation, the vortex vibration is critical. We have at least 3 universities of hundreds of tests to make sure there is no vortex vibration.
Okay, thank you.
Yeah.
Following Mingming's question, I have one more question. What is the structure of the auxiliary cables, and how does it differ from a cross cable?
Unlike the cross the cables sharing the self-weight of girder segments, auxiliary cables themselves bears almost no self-weight of girder segment. It merely provides a small initial internal forces. Accordingly, auxiliary cables are only arranged to improve the vertical stiffness. The second difference is the anchorage location are different. Auxiliary cable are anchored on the middle transverse connection box, where regular stay cables are fixed at the outside the ferry, the two sides, transverse two sides. That's all.
Thank you. So without that bridge, how people drive from this side to the other side? So please show us the
They
map of
have to
the areas.
they have to go to the Yamen Bridge.
So
which is-
please show us a slide from your point.
Yeah, maybe, yeah. Oh, I wait a moment.
Okay.
Can you
Yes. Yes.
can you see the slide? Yeah.
Yes.
Okay. 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 哎，怎么动了？Sorry. 怎么不会动呢？There is something wrong with my PowerPoint. It's stuck here. I'm sorry. I have to.
Fine, we can wait. Take your
turn-
time.
Okay. 不会动了。哦，再看一遍吧。Okay. I'm sorry. Wait a moment.
It's okay.
Okay. Okay.
Yes.
Yes. Can you see the? Okay. Can you see the point?
Yes, maybe the first two slides.
我要看看符号。啊，是睡觉吗？有没有？还是睡觉吗？不是。Can you see the point?
Yes.
Okay, you can see this corner. Without this Huangmaohai Link, you have to go to the green road upside to the Yamen Bridge and get down. And we choose the Huangmaohai Link can save 30 minutes.
Okay. So
Okay.
they don't have to turn around of this
Yes.
space. Okay, let me see if there is some questions from the audience. No. So I have some more questions. So please, what is the structure of elastic cables and how they are anchored?
Okay, the elastic cable is a special.
So please show us with the slides.
Yes, can you see this?
Yes, but a different slide, I think. It didn't change.
It didn't change.
Yeah.
Maybe I will.
多种那个共享的时候选择桌面会那个好调一点。
看到了吗？Can
Yes.
you
哦，
can you
可以
see
了。
the slide? Yes, this is illustrated cables. This is the electric cables. We have 8 electric cables. 4 above the deck and 4 below the deck. One end is anchored in the cross beam. The other is anchored in the pylon. Why we choose elastic cables? There's 2 reasons. If we without restraint, the bridge will move too much. Where we use regular restraint, some like a bear, it was to regulate when the earthquake comes. The seismic forces is beared only by the central column, central link pylon. It is too much. But with electric tapes, we can make sure that seismic forces is shared by all 3 pylons. That's why we use restraint, but not too regular. So it's illustrated cables.
Will it move with the temperature change? It will move with the deck?
Yes. If temperature changes, the deck and the tower is fixed together because with the wind it extends 2 ways to the approach bridge side, but fixed in the middle. But when the earthquake comes, it is flexible. It can change. We want to be fixed in temperature and static, but movable to earthquake seismic forces. Am I clear? Okay.
Yeah, I understand.
Okay.
So is that the pilot is very nice appearance. So it's a hyperbolic variable cross section. Am I right? Is it?
Yes.
So the construction will be quite challenging, I think. So any other solutions for these pylons? So why you choose this very sophisticated appearance pylons? So the reason is the aesthetic was the major reason, or you have other reasons?
Yes, for sure. Aesthetic is a major reason, but there's also other considerations. During the design phase, automated design such as A-shaped pylon, H-shaped pylon were all taken into consideration. Nevertheless, you can see there is a 5 pylon. If we choose H pylon, there will be 10 columns around this area. This is too much. It's excessive number of columns, which spoil the overall landscape. This is a aesthetic aspect. On the other hand, if we choose H pylon have 2 columns, which one column is small. It will bear less in the shape collision. If we combine the 2 columns into one, it's bigger and huger in the below. It can bear more collision forces, and also with this design, we can achieve better aerodynamic performance.
And how do you build this very sophisticated pylons? How about the formworks and the construction method? Is it cast in situ or prefabricated for segments installation?
It is cast in situ, but we fabricated the whole cage. You can see the rebar cage. The whole cage is fabricated and integral hoisting to the tower. But the concrete is poured and constructed inside.
So because the section is varied, so the rebar cage is also has to adapt this form. So how do you challenge this kind of too many variables to suit the appearance?
Yes, the rebar cage is a difficulty. So we implant the 3D design model. We use the beam technology and fabricate in the factory. But the more challenging part was the formwork.
Yes.
Because the concrete always changing how to use the formwork. Because if you use the steel formwork, you have to change it constantly, and it was very expensive. So we figure out to use the wood formwork, and we finished the 14 5 segments only with the 3 set of formworks, because
Oh.
the 3 set of formworks of wood is also changeable, but it can accommodate to the variety of about I will give it 50 meters. We have to change another formwork.
Oh, difficult. So I'll check if there's any. So you use separate box section for the deck. So for as I know that many long span bridges use box sections for box girder for this bridge. So you use separate 2 box sections. So why do you choose this solution comparing to other bridges to use this?
Yes, first, it is suitable to the single column pattern. If you choose a single pattern, you have to choose the split turn box. And the steel box girder of Huangmaohai is have a tremendous width of the transverse. The width is exceeding 50 meters. Is trimming wide, and the transverse connecting box is 11 meters wide. So consequently, the structure exhibit low transverse stiffness. The main challenge is to lengthen the large transverse dimension and the hoisting stability control during the vibration. It's too flexible. It's too large and only restrained by the small connecting box, transverse bucket. So it's too flexible. We have to control it, make sure it's it's our design purpose.
Okay, I got a question from the audience. His name is Wilson from Tongji University. Thanks for the presentation on this case study. I usually see many bridges using double pylon. Why did you choose a single pylon? That is his question.
Thank you for the question. As I just answered Dr. Xu, Professor Xu, we have taken into consideration A-shape pylon or H-shape pylon in the design phase. But there is 3 reasons we choose the single pylon. First of all, of course, as aesthetic. You know, there is the 2 bridges of this project. The Huangmaohai Bridge and the Gaolangang Bridge. One bridge is 3 pylon. Another bridge is 2 pylon. There is the total 5 pylon in total. If we choose H pylon, there will be you can see this picture. This is can you see the slide?
Yep.
Yeah, this is a 5 column pylon. Yes, it's already too much. But if you choose the H pylon, it will be 10. It will accelerate and spoil the landscape. This is the aesthetic aspect. The other aspect is is pollution, anti-pollution, because if you split one column into two, one big into two small, the two small column have two small foundation. When the shape comes aspect, the collision force will be too much. But if you combine the two columns together, the anti-collision ability is improved. So this is the second aspect. The third aspect is aerodynamic. It's one column. We can choose a split twin box girder. It have more higher aerodynamic. There's three aspects reason.
Okay. So I will get one more question. I think this will be the last question from the audience. From Dimitri Yankin. He said, thanks for a lot for the presentation. How did you stabilize the middle pylon during two-side cantilevering? Did you use any temporary cables to fix the top of the pylon?
We use auxiliary cables, not temporary cables. We use
in the construction, in the cantilevering construction.
yeah. Maybe I can share the 哪个是屏幕？整个屏幕。OK。We address this question. This three slide, PPT slide, because the three pylon cable stay bridge has less than the restraint anchorage for the central pylon. It have a poor vertical stiffness. There is a lot of approaches to solve this question. There is a cross cable system used by the Queen's Ferry crossing, or the high used by the Mercy Gate Bridge. Also, there are 10 another solutions, include add auxiliary pair, increasing split cable area, increasing metal dimension, and so on. And after comparison, we determined that 5 auxiliary cable solution features the lowest cost. So we choose
Oh no,
5.
the question is he asked during the construction, 在悬臂施工的时候有没有stabilize the middle pylon?
Yeah. Sorry. Yes, we do have some measures, because when the cantilever construction structure, we have typhoons, so we have to make sure the structure is stability. We use temporary pier plus TMD combined control technology to make sure that, and the system has performed well during Typhoon Marias, when the structure withstood level 8 wind during 300 meter cantilever construction. Okay.
Due to time limitation, I have to close the webinar. Thank you very much, Mr. Zhao, for the presentation. And thank you for all the audience and the questions. So I closed this webinar. So goodbye, everyone.